Hello, my name is Isamu Poi, and today I will present our work called Interactive Debugging at IP Block Interfaces in FPGAs. This work was co-authored with Marco Merlini and Professor Paul Chow. FPGAs have been proven effective in data centers, but debugging support is sorely lacking in this environment. We try to fill this gap with a new open source approach to FPGA debugging that prioritizes interactivity. Typical FPGA debugging is done with an embedded logic analyzer. It saves logic values in an on-chip buffer, which you can then look at in a waveform viewer. This only provides a small window into your design, and it's up to you to interpret the signals. If you want to look at something else, you need to move the ELA and resynthesize. This can feel like cleaning a whole building with a toothbrush. We observe that many designs look like data flow graphs, and that it is much more intuitive to reason about transactions between nodes rather than interpreting dense waveforms. Our work is a simple pass-through module for manipulating these transactions, and we call them debug governors. To use them, place a governor between any two endpoints. They can accept commands and log values to a common output. Let's look at a governor more closely. Suppose we wish to debug the messages from a sender named Alex to a receiver named Brittany. The stream is passed through a debug governor, which offers four debugging operations. Pausing prevents Alex from sending data. Logging duplicates data from Alex to a third output. When dropping, Alex can send data freely, but nothing will reach Brittany. Injecting allows the developer to send arbitrary messages to Brittany, pausing Alex if necessary. Most importantly, debug governors can enable any simultaneous subset of these operations. For example, single stepping. Alex starts out paused. And when a step command is received, a single message is sent to Brittany and logged. Pausing is automatically re-enabled afterwards. In our experiments, we have found single stepping to be intuitive and extremely helpful. This diagram shows the internals of a debug governor. A control FSM listens to commands and activates control inputs. A width adapter forces logs to be 32 bits wide. This allows you to debug many different streams and still keeps the interconnect simple. Finally, the centerpiece of the debug governor is something we call a handshake governor. This module is what actually manipulates transactions. It is made up of a chain of 4 circuits, one for each of the pause, log, drop, and inject actions. Any subset can be active at any given time. A simple debug governor has only one handshake governor. But we can compose them together in powerful ways. For example, in the paper, we discuss how to make a debug governor for a memory mapped bus. We believe that debug governors are a simple approach to higher level debugging. They are very lightweight. You can place them on all streams at once, which means you never need to recompile, and we strongly believe that the interactivity enabled by the debug governors is very useful. Like any debugger, the governors are not without disadvantages. When active, governors do influence transactions, and bugs can appear or disappear as a result. Also, we currently do not support cycle-accurate injections. Looking back, governors focus on functional debugging, but colleagues and industry professionals have also expressed a need for performance debugging. On a different note, our approach works at a higher level and might only find the rough location of a bug. The idea is to quickly target where something like an ELA can then be added. For future work, we could add per governor buffers for logs and injections. This could make more performance debugging possible, but costs more on-chip resources. Finally, we want to try applying our new approach to other protocols, such as Avalon or Wishbone. That ends our presentation. Thank you for listening, and if you have any questions, please email us for any inquiries.